In this video, we're going to talk about the independent samples t-test. Specifically, we're going to talk about two major points. We're going to discuss the logic of the independent samples t-test, and then we're going to also provide a full example of the independent samples t-test. First, the logic. As always, you start with a major population that's too big for you to study the whole thing, so you take a sample. In this situation, we do not know the population parameters. From the sample that we took, we divide that sample into two different groups. Frequently, the best way to do this is by using something known as random assignment, which simply means that you take everyone who's in the sample and through some random method you decide who goes into group 1 and who goes into group 2. The whole purpose of that is to try and get two groups that are roughly equivalent on everything. You want two groups that are very, very, very similar. We call that initial equivalence. Before you do anything to them, you want them to be the same. Then what you do is you treat the two groups. Group 1 gets something called treatment 1 maybe, and group 2 gets something called treatment 2. That could be anything, like treatment 1 could be a control group, or could be a control treatment, and treatment 2 could be a drug. Or they could be two drugs, and you want to see which one is more effective. Doesn't matter. You're treating the two groups in different ways. Then after the treatment, of course, you measure them, and you're interested in the mean of each group. Now, if the two groups are equally effective, these two means should be the same. It's important to remember that this sample mean right here is trying to represent what this population would be like if everyone in that population was given treatment 1. So this sample mean is trying to represent a theoretical population, or a population that was all on treatment 1. In other words, it's trying to estimate what the mu sub 1 would be, what the mean of the population would be if everybody got treatment 1. Similarly, this mean down here is trying to represent what this population would be like if everybody were on treatment 2. It's trying to represent mu sub 2. And of course, the null hypothesis is that these two population means would be the same. Again, we have to work with these two sample means over here. And if there's any variability between these two sample means, there's two things that might be causing that, right? It might be sampling error. Maybe these groups weren't initially equivalent because of sampling error. Or maybe this difference, if there is a difference, is created by differences between the two treatments. And again, that's what we're trying to find out. Which of those two possibilities is more likely to be true? Now we're going to do an example. Is treatment 2 more effective than treatment 1? We're going to use an alpha value of 0.05. Here is some information that you need to know about group 1 and group 2 in order to run the statistic. Group 1 has a mean of 10, a standard deviation of 4, and had a sample size of 11. Group 2 had a mean of 15, a standard deviation of 5, and a sample size of 11. So the first thing we need to do is state the null hypotheses and the research hypothesis. The null hypothesis is going to be mu sub 1 is going to be greater than or equal to mu sub 2. This is a one-tailed test because of the way the question is asked. Is treatment 2 more effective than treatment 1? Since I'm saying I'm only interested if treatment 2 is more effective, then this is a one-tailed test. I didn't ask, are the two treatments different or are they the same, which would be a two-tailed test. This is a one-tailed test. And so the null hypothesis, of course, is stating that the two are equal, or group 1 is going to have a lower mean than group 2. That's the null. The research hypothesis is stating what you're actually trying to test, right? It's the fact that the mean of group 2 is going to be higher than the mean of group 1. It's really specifically saying that the population under treatment 2 would yield a higher score than the population under treatment 1. That's what it's really talking about. The next step is to find the critical region. We do that, of course, by computing the degrees of freedom. The formula for the degrees of freedom with an independent samples t-test is the number of people in group 1 minus 1 plus the number of people in group 2 minus 1. Now these two group sizes do not have to be the same. They frequently are, but they don't have to be. In this case, it's going to be 10 plus 10, which is going to give us a degrees of freedom of 20. And then we have to look up that degrees of freedom in the appropriate table in the back of the book, and we're going to find the critical value is 1.7247. And I know that this is going to be a negative critical value because the statistic always takes M1 minus M2. And since I'm predicting, the researchers are predicting, that treatment 2 is going to be higher, I'm going to want to have a negative critical value, because if you take 1 minus group 2 and 2 is going to be higher, you would end up with a negative number if the treatment 2 is more effective. So I want to have a critical value on the negative tail. Here's a picture. If I get anything in this region, then I'm going to reject the null. The next step is to compute the test statistic. This is the statistic we'll use, the formula we'll use for the independent samples t-test. We need to find the mean difference, and we have the mean, so that's not a problem, but we also need to find the SEM. The SEM for an independent samples t-test uses this equation. And in order to find this equation, we need something called the pooled variance. That's what these two terms are. Those two terms are the pooled variance. And that term also has an equation, and that's this equation. So we need to find the pooled variance first, then we substitute that number into the standard error of the mean equation, and then we take that number and substitute into the t-test equation. So using the information that was given to us on the previous screen, the sample size minus 1, right here, is going to be 10. The standard deviation of sample 1 squared is going to be 4 squared. The sample size minus 1 for group 2, that should be a little subscript 2 there, is going to be 11 minus 1, or 10. And the standard deviation for group 2 is 5 squared. And then the denominator is n minus 1 for the first group and n minus 1 for the second group. When we work that out, obviously 4 squared is 16 times 10 is 160. 5 squared is 25 times 10 is 250. And then we add the numerators together, or not the numerators, the two numbers on top together, and divide by 20, and then we're going to get 20.5. This is our pooled variance. This is the number we need to substitute into this equation up here. When we substitute in the numbers that we have this equation. When we run through those numbers, we end up with 1.931. That is the standard error of the mean. That is how far apart we expect these two sample means to be simply due to sampling error. We expect them to be about 2 units away, 2 points away from each other, just due to random chance variance. So we take that number and we substitute into the equation above. So this is the mean from group 1, the mean from group 2, and then the sampling error. When we run through those numbers, we find an obtained t-value of 2.59. That is the obtained t-value. Notice that it is a pretty high number, and what we need to do is we need to find out, is it in the critical region? Well, here I've redrawn the critical region from the previous screen, and yes, it is. Oops, I should note that it should be negative. And so yes, it's over here in this region somewhere, and so we are going to reject the null. That means that indeed it is true that treatment 2 is more effective than treatment 1. The next step is to compute the effect size. We use this equation, the mean of group 1 minus the mean of group 2 divided by the square root of the pooled standard deviation, or excuse me, the pooled variance, so we can get the pooled standard deviation. When we do that, we end up with a D of 1.1, which is a large effect. And now we need to summarize the results. Those getting treatment 2 scored higher than those getting treatment 1. And then I have statistical information. And then I have something to help interpret the results. Treatment 2 led to scores more than 1 standard deviation higher than treatment 1 scores. So that's helping the reader this second sentence is helping the reader understand the size of the effect. You're helping them interpret the results. This first sentence is simply saying, is it likely to be due to sampling error or not? Is this mean of 15 and this mean of 10, are those likely to be different? Is the size of that difference likely or unlikely due to sampling error? Because we rejected the null, we're saying it's unlikely to be due to sampling error, and it's probably because treatment 2 is more effective than treatment 1.